Thank you all for attending my talk today, which is on the ability and value of collecting time-integrated indoor and ambient air samples to provide an average concentration over a longer time period than can be achieved with other methods such as summa canisters. Beacon provides the industry's gold standard sorbent samplers for the collection of time-integrated samples. These passive samplers, which have been applied by Beacon on U.S. Department of Defense facilities, residences over solvent plumes, petroleum refineries, dry cleaners, and elsewhere, provide average concentrations, typically over days or weeks, to assess vapor intrusion risks and inhalation risks from ambient air. Beacon provides the passive samplers via test kits for our clients to collect the samples following simple field procedures. And following sample collection, the samplers are shipped to Beacon's accredited laboratory for analysis. I'll be sharing with you today Beacon's experience with this methodology and some of the research and product applications performed to date. I see that we have attendees from around the globe, so I thank you for taking the time during the day or evening, as is for some of you, to attend my talk, which will take about 35 minutes. We'll then have time for some questions, so let's get started. So passive sorbent samplers allow you to collect indoor or ambient air samples over hours, days, or even weeks. The ability to collect time-integrated measurements over longer time periods than is possible with summa canisters allows for time-weighted average measurements that may better represent actual risks from vapor intrusion or inhalation of ambient air. Ongoing studies suggest that vapor intrusion is episodic. That is, intrusion of vapors occurs periodically into a building and not consistently. Therefore, by collecting samples over days or weeks, you are less likely to miss contamination during a vapor intrusion event, and conversely, provide a more accurate average measurement that normalizes the highs and lows. As you can see on this slide, temporal variability of indoor air concentrations is very often the norm. So looking at this, on what day would you collect your 24-hour sample to assess whether there is a VI risk at this home? What if you could collect a sample for several days or even weeks to get that time-integrated measurement that will provide an average concentration? Passive samplers provide you with this ability and are easy to use. They're less obtrusive than using summa canisters, which we in fact get very good feedback from our residents as compared to when they're asked to leave a 6-liter summa canister in their home. And sorbent samplers provide high-quality data while achieving low detection limits, and they can target a range of concentration that spans orders of magnitude. So with a talk today, we'll be going through a little bit about Beacon first, just give an idea of our experience and who we are. And I want to talk to you about some US EPA guidance documents that have been released within the last year or so that put a focus on collecting time-integrated measurements. We're going to talk about the benefits and limitations on using passive samplers and discuss how they operate, and the importance of the quality control and the design of it, as well as the analysis to make sure you're not only getting accurate results, but reproducible results. And we'll show some comparisons of the using passive samplers to summa canisters to show the accuracy of the method, as well as a lot of duplicate results to show its precision. And then we'll wrap up by looking into considerations of how you do collect passive samplers in homes. All right, so to put a face with a voice, there's a picture of myself. I started Beacon in 1999 with the focus of specializing in the identification of trace levels of organic compounds in air and soil gas using sorbents. And that is the focus of what Beacon does day in and day out. So we're running more sorbent samplers than probably anybody else in the United States and potentially internationally. We provide our services throughout the United States and across 6 continents through the use of test kits for our clients to collect the samples and send them back to Beacon for analysis. And we've been doing this for quite a while. I started Beacon in '99, as I noted, but myself and others have been working on this type of applications for more than 25 years. So bring a lot of experience to your project. So what is Beacon? Beacon is a laboratory. We're not a consulting firm. We're a laboratory that uses sorbents to target trace levels of compounds in air and soil gas. And we are an accredited laboratory. In fact, we are accredited in accordance with ISO 17025, state and ELAP programs, as well as the U.S. Department of Defense ELAP program, which if you're familiar with that program, you know it's like ISO 17025 on steroids, very stringent in the quality control requirements. And we're very proud that we are accredited for method A260C, TO17, TO15, and the new EPA method 325, which we'll be talking about further here in a little bit, which deals with targeting benzene in the air around petroleum refineries. So we are an accredited laboratory for each of these methods using sorbent samples, and our accreditations are for these methods without modifications to them, which other labs are not able to achieve. We're also accredited for not only the sample collection for air and soil gas samples, but also our process for how we condition sorbent samplers and send them out in kits has gone through the accreditation process to make sure that what we are producing at the end of the day is defensible data for your project. All right, so let's talk about the recent developments in the United States from the EPA in their interest of using time-integrated measurements to get an average concentration. The EPA's vapor intrusion guidance document, which came out in June 2015 as final, includes in there the use of sorbent samplers to collect a time-integrated measurement to make sure that contamination is not being missed for air samples, for indoor air. And it recognizes the temporal variability, which has been identified in a lot of research that's ongoing, that's been completed over the last 10 years. In addition, last year, the EPA released a new technical paper, which a copy of it can be found on our website on our resources tab. But in this paper, it describes how to use passive sorbent samplers to collect indoor and ambient air samples. And then, even most recently, the EPA produced a new method, which is method 325, which is for the collection and analysis of benzene in air around petroleum refineries. And to talk about that a little bit further, with this method, it requires the use of passive sorbent samplers to sample the air around petroleum refineries for emissions of benzene. It's a very prescriptive method. You have to use sorbent tubes or specific adsorbents you have to use, and it just dictates the number of samples you have to collect and the QC that has to be followed. Basically, in a nutshell, you have to have at least 12 sampling stations around the perimeter of the petroleum refinery, and that underneath each of these stations, these shelters, which you can see a picture of it here on the slide, is nothing more than a PVC cap in this case with a sorbent tube placed beneath it. You leave these sorbent tubes out for 2 weeks, you take it down, and you put another one up. So you're continuously monitoring the air around the petroleum refinery throughout the whole year with 2-week intervals. And this method is going to be required of all petroleum refineries starting January 2018. And currently we are working with the refineries to do their pilot tests to make sure that they have their emissions under control. So you can see from these guidance documents, just came out in 2015, there's a big emphasis in the United States through the EPA to promote the use of getting a time-integrated measurement. And we'll discuss further why that's important. All right, but first let's talk about the different types of samplers. There's basically 2 classes of passive samplers. There's a radial type sampler shown on the left, which that is the Radial technology. And then there's an axial sampler shown on the right. Sorbent tubes, stainless steel tubes filled with adsorbent, or Beacon's sampler, which is a glass vial that has sorbent traps inside of it. The difference between them is how they absorb compounds. With a radial sampler, the gases will diffuse onto the adsorbent from all sides. So it has a higher uptake rate because it has more surface area that's exposed to the air. An axial type sampler has an opening at the end of the tube or the vial that allows for only one direction for gases to come into the sampler. So it has a slower, but also a more predictable uptake rate and allows for the ability to be able to provide concentration data over even a longer time period. With a radial type sampler, it is more appropriate for a short duration, or with an axial sampler, while you can do a short duration, as long as you can meet your detection limit, you also have the ability to leave these samplers out for weeks and even months. All right. All right, so let's talk about the principles of how these operate. Basically, gases want to move from an area of high concentration to low concentration and that's following Fick's law of gas diffusion. Diffusion is nature's pump. It causes the compounds in gas to move from the area of high concentration to low concentration. And with a sorbent sampler, you have adsorbent inside of it that acts as the sink, as where there is a zero concentration, because once the compound is close to the adsorbent bed, it will be absorbed, and now you have a zero concentration right at that adsorbent air interface. So that is the driver of how these samplers work. Very simple, but what we have found is it's very reproducible, and that the diffusion of gases will move in a very predictable pattern. Okay, so with a passive samplers, we're measuring the mass that is on the sorbent sample from its exposure in the site. But how do we know what the rate of absorption was? Well, that is based on what the uptake rate is. So in this equation, you have C, which is the concentration here, micrograms per cubic meter, which is equal to the mass divided by the uptake rate in milliliters per minute times the time. And then it's multiplied by 1,000 to correct for the units to be able to report nanograms to micrograms per cubic meter. But knowing what the uptake rate is very important for this type of sampler to work. Fortunately, there's been a lot of work done on this over the past multiple decades, particularly in Europe and elsewhere in the world, to determine what these uptake rates are. But you're even able to determine what the uptake rates are theoretically. To determine uptake rates for a sorbent tube's axial type sampler where gases enter on the open end, you can use an equation that will calculate a theoretical uptake rate. So here you have U being the uptake rate milliliter per minute is equal to the area of the opening of the tube divided by the diffusion gap from the opening to the sorbent bed and multiplied by the diffusivity coefficient in air for the compound of concern. And there's been a lot of work done for most compounds that you'll have to target where we know what the diffusivity coefficient is based on the previous work. So the question is then, how does that calculate out? So here we've taken some examples of some chlorinated compounds we routinely target, and by applying the diffusivity coefficient in air, the area of the opening, and the distance for a standard axial sorbent tube, which is 15 millimeters, we calculate the uptake rate here to be from 0.53 milliliter per minute to 0.8 milliliter per minute. So the question is, how does that compare with what has been measured through studies empirically? So we look at the theoretical uptake rates we just calculated and compare them against work that has been done over the years and that's published, which is available in different guidance documents. And we can see, looking at the relative percent difference between the theoretical and the measured uptake rate, that there's actually very good agreement, that it does behave in a very predictable fashion. Now, one thing about these uptake rates, a lot of the work has been done based on 8 hours and 24 hours because they've most often been applied for OSHA applications, which is for occupational safety and health, where you're not looking at long-term exposure, but short exposures. So Beacon decided that it was important to be able to demonstrate, while we believe that there would be good agreement, to demonstrate that this type of sampler will work for long duration sampling. So working with Matt Bates with the MCBA in Wales and the Health and Safety Laboratory in the United Kingdom, we started an evaluation of different sorbent samplers over a longer duration period, where we sample for 1 day as well as 7 days, 14 days, and 26-day periods. And we use different adsorbents that Beacon has determined work well for targeting compounds and able to retain the compounds once they've been absorbed for a long time period. And we also use Carbopac X, which is the adsorbent that the EPA has recommended for the method 325 benzene Fenceline monitoring program. And also there's been some work published on that adsorbent for longer duration sampling for 1 day as well as 14-day uptake rate studies. In our study, we challenged the samplers with both the BTEX compounds as well as chlorinated compounds. So here's a setup of what the test site looked like at the Health and Safety Laboratory. So you can see it was not done just in a shed. what you have is a very sophisticated process for being able to dose a exposure chamber with known concentrations of the compounds of interest, and to be able to measure them throughout the whole 26-day exposure period. And I'll note that each of the samplers that we tested there were done in replicates of 6. So there were 6 of each one to make sure that we were able to evaluate the precision of the uptake rate as well. And so what did we find? Here is a slide that shows the results for Carbapac X for the BTEX compounds, benzene, xylene, and toluene here being shown. And what I want to show you here is that there's EPA published uptake rates for benzene using Carbapac X, as well as for xylene and toluene. And there's also a study that was done by Martin et al. In 2003 that determined the uptake rates for these compounds as well for a 14-day period. And you see there was pretty good agreement between the 1-day and the 14-day. And so what Beacon added to this body of knowledge is the uptake rate for 7-day, 14-day, as well as 26-day. And as you can see, there's very good agreement in the uptake rate for each of these compounds. And so we're able to demonstrate that you can use this sorbent tube in this configuration, the axial configuration, to target these compounds for up to 26 days. And we would contend you can even do longer than that. But at a minimum, 26 days, and you will have a consistent uptake rate. So to further demonstrate the consistency, we plotted a lot of the results for the compounds we're targeting. And what I want to show you here is some results for the chlorinated compounds, because they are most often of concern for vapor intrusion sites. So this slide and the next one show the linearity of the uptake rate for various compounds using sorbent tubes with proprietary adsorbents that we chose for this study. And what you'll see here is that the uptake rate, the mass that was absorbed, was linear by time, by 7 days, 14 days, 26 days. Here it is again for 1,1 DCE, 7 days, 14 days, 26 days. And you'll see that pattern repeats nicely for each of these compounds that were targeted, as well as for these additional chlorinated compounds. And there's more compounds in this that were included. They all had very good linearity in their uptake rate for the chlorinateds and the BTEX compounds that we targeted. And we'll be continuing doing more of this research work to prove ourselves and to use more advanced adsorbents that have not been evaluated in the past. And we believe that there's importance to use some better adsorbents that have come available in the last 10 years or so. Okay, so we've demonstrated and shown here that there is linearity with these sorbent samplers, that you can sample for a longer time period, for several weeks. But how low is the detection limit? So with Beacon's method, which is, as we noted, accredited, and so we have limit of quantitations, limit of detections, and detection limits that are accredited of what we're able to achieve with these compounds that we're targeting. And for the 60-some compounds that are in our scope of accreditation, which you can see on our website, we are able to achieve a detection limit for each of those compounds at 2.5 nanograms, and a limit of detection at 5 nanograms, limit of quantitation, which is a low point of our calibration curve, at 10 nanograms. Why is that important? Is because we can report data with low detection limits with a high confidence level that will be defensible. So for example, for a 14-day exposure period for trichloroethene, the limit of detection is 0.5 micrograms per cubic meter. Whereas for a 26-day exposure period, the limit of detection, of course, will be about half, because the time that's in the equation for calculating the concentration is in the denominator. So the longer the sampling period, the lower the detection limit. So we're able to achieve pretty low detection limits with using these sorbent tubes. All right, so we can achieve lower detection limits. There's a linearity to the uptake rate, but how does it compare to other sampling methods? Here's some work that we did early on where we're comparing using sorbent tubes to summa canisters. The sorbent tubes, which we show here as method TO17, were exposed to air inside of a commercial building for 14 days. The TO15 samples were collected over a 24-hour period at the beginning of this 14-day sampling period. And this was not at a residence house, this was at a commercial building. In fact, it was at a Navy facility. And as you can see there, through evaluating the relative percent difference between the two data points for tetrachloroethene and trichloroethene, which were of concern at the site, there was excellent reproducibility. 3.4, 3.4 with 0% RPD. Doesn't get much better than that, right? But even if you look across here at all the different concentrations were identified, the biggest difference here was 1.8 versus 1.3, 32% RPD. Still very close, and considering that one was for 14-day sampling period and the other was for 24 hours, I'd say it's very excellent reproducibility. Further, you note here, even at J values, which are measurements that are above our limit of detection but below our limit of quantitation, we still had very good reproducibility between the two methods. And to note that Beacon did the analyses for the sorbent tubes and a separate contract laboratory did the analysis for the Summa canisters. All right, so then let's take a look at the precision of these samplers. We looked at the accuracy comparing between two different methods. Now let's look at the precision, where we're looking at replicate samples, duplicates. On the left are the results for two sorbent tubes that were exposed to air for 14 days. And here we have Summa canisters that were side by side, where the samples were collected for 24 hours. And inside these red boxes are the relative percent difference between the two paired samples. So the first box shows the relative percent difference for the sorbent tubes, where you see that the highest difference between them was less than 8%. And then for the Summa canisters, which were sampling side by side in the same room, you'll see that there was a relative percent difference that had the lowest amount greater than 8% relative percent difference. So I point this out to see that there's a lot of precision with using sorbents, and there's a lot of consistency and because of its design as well as the efficiency of the analysis, where with sorbent samples, we are desorbing the whole sample onto the system, where with a Summa canister, you're just pulling an aliquot out of the can. You're pulling milliliters out of the liters of sample. And so there's different variabilities to that process that may not produce data that gives you as great as precision as using sorbent methodologies. All right, here's some more precision data. As I mentioned with method 325, we're sampling around the perimeter of petroleum refineries, and we're getting samples back every 2 weeks for these clients' pilot program. So we're constantly getting samples back. We're running these sorbent tubes daily. And with the method, the requirement is that you have to do duplicate samples for each sampling event, and it has to be done at 10%. So we're getting lots of duplicate results back. Here is an example of what we're seeing and what we are routinely seeing. Of these 11 rounds of sampling, here's round 7 out to round 18, which was the last round at the time I pulled this data, you can see the max relative percent difference between the duplicate pairs. Here's a duplicate pair here at location 4 and a duplicate pair here at location 13, where you have two sorbent tubes sampling side by side. The greatest difference between any of the pairs was 9%, which once again shows very excellent precision of the method. And that is both in its consistency in the uptake rate when it's out in the field, as well as the analysis back at the laboratory where Beacon is performing these analyses. And keep in mind that these are samples that are collected outside, often in very humid conditions, such as in Houston, Texas, if you're familiar with the climate there. So these samplers are being exposed to differences in temperatures from day and night. They're exposed to wind change differences, speed of the wind, moisture levels. They have rain events, but yet these two tubes out there sampling for a 14-day period consistently absorb compounds that's in the air. So once again, very precise method by using sorbent samplers. All right, so that was at low concentration, but let's take a look at higher concentrations. This is from work that we did in a former dry cleaner, which was now being used as an art studio. So tetrachloroethene was the contaminant of concern as far as vapor intrusion, but they also had some compounds of interest in the room because they had other products being used. And so what you'll see here is not only do we have very good relative percent difference between these pairs of sorbents hung side by side in the air with a relative percent difference that was no greater than 8%, but look at the concentrations that were identified. We had concentrations as low as 0.6 micrograms per cubic meter, but we also had concentrations of tetrachloroethene that were at 300 micrograms per cubic meter. And you look at the difference here, and the relative percent difference between the measurements had fantastic correlation. So demonstrate to us early that with these sorbent tubes, not only do they provide precise measurements at when there's low concentrations present, which is often what we see in indoor air, but also even at high concentrations. And that's what we've known for decades working on OSHA sites where it's a commercial manufacturing operation where they're using solvents inside the buildings where they use these sorbent tubes to monitor the indoor air for the workers. So once again, excellent reproducibility while using the sorbent tubes, even with orders of magnitude difference in concentrations. All right, so we've shown you what the sorbent samplers look like, and let's talk about the analytical method. The analysis is done by Beacon by method TO17, US EPA method TO17, which is using sorbent tubes introduced by thermal desorption onto the gas chromatograph with identification of the compounds by mass spectrometer. There's different detectors that can be used, a PID, an FID, an ECD, but Beacon uses mass spectrometry for compound identification to provide data of the highest quality. And with this method, you have all of the QC checks that go along with this mass spectrometry method, which is having the internal standards and having the calibrations and being able to report level 3, level 4 data quality packages. So you can produce data that's not only accurate, but very defensible by using mass spectrometry as the detector. And the compounds that we're able to target range from vinyl chloride out to 2-methylnaphthalene with our standard list of compounds. And this is in a chromatogram showing all the compounds that are in our calibration for TO17 for our standard run. Now there are compounds that cannot be targeted with sorbents, and it's important to note this. Methane, ethane, ethene, acetylene, those compounds, C1 to C2 hydrocarbons that are just too volatile, that will not be absorbed by adsorbents, cannot be targeted using sorbent samplers. You will have to use a whole air method such as summa canister, Tedlar bag, or syringe to be able to identify compounds in gas when you're targeting those very volatile compounds. But I will say with the sorbents, while this is our standard run out to 2-methylnaphthalene, we in fact can extend the run and even target heavier pHs and other SVOCs using adsorbents because of its ability to trap heavier compounds and then for us to be able to identify it with our analytical method. Note though that this chromatogram here showing vinyl chloride out 2-methylnaphthalene, those would not, you cannot be able to target both of those compounds at the same time with one adsorbent because the adsorbents have affinity properties for a different range of compounds. One adsorbent that's good for vinyl chloride will not be good for 2-methylnaphthalene and vice versa. So this is something important to keep in mind when you're designing your sampling plan and working with the laboratory that'll be doing the analyses. Okay, I want to share with you now some ongoing research that we're doing. As Lowell mentioned, we work with universities and we've worked with numerous universities over the years to further understand and determine the capability of sorbent sampling for both indoor ambient air as well as soil gas. And this here is a picture of Dr. Paul Johnson's study house out in Utah, where he has created that house into a research facility where he's taking samples daily of the concentration indoor, subslab, soil gas, as well as monitoring the variables that exist, such as the temperature inside and outside the house, the pressure inside the home, subslab pressure, the wind speed, the wind direction, precipitation, and other variables to try to understand what causes vapor intrusion to occur. And this work currently we're doing is we're working with Dr. Paul Lin and Dr. Yanming Guo for demonstrating the ability to collect a long duration sample and how using passive samplers and how that compares to taking daily 24-hour samples. Okay, so the importance of long duration sampling, as we know before, is that there's a lot of temporal variability. Here, these graphs show some results from this home. As you can see in the winter months, there's a lot of variability, but there's lots of vapor intrusion occurring. But in the spring months, there's less vapor intrusion. However, there's still episodic events. So the question is, at what day would you take your 24-hour sample? And that's important to note because you have a risk of not being able to report a concentration that accurately represents the risk to residents at that home. In fact, with Chase Holton's publication in Environmental Science and Technology 2013, he summarized from all the data that they collected out there that there is a high potential for a false negative resulting from vapor intrusion by just taking a short-term sample over 24 hours. And in addition, there's a high potential to incorrectly characterize that long-term exposure by only taking that 24-hour sample. So there's about half of all the 24-hour samples would come back as a non-detect when they did a statistical evaluation of the thousands of data points they collected. So basically you have a coin toss, a 50% chance that your result from your daily sample that you took would be within a mean concentration of 1 order of magnitude from the true mean concentration at the site. So is there a better way to sample out there to make sure that you're not missing indoor air contamination when it's present? So that takes us to what we're doing out there. And I'm going to show you 4 slides here from the first 4 rounds of sampling, which just started this year. And there'll be a lot more data provided over the next year or 2. In fact, this is a 2-year program we just started on. So what we're doing out there is we are exposing passive samplers, and we're using the sorbent tubes that I showed you before, as well as Beacon's passive sampler that's shown here on the right, which is a glass vial that contains sorbent traps inside of it. And what we're doing is deploying the passive samplers on the first day of the sampling interval. In this case here is a 26-day sampling interval, where Dr. Guo and Dr. Darlene are collecting 24-hour samples every day while the passive samplers are exposed to the indoor air. So what you see with that blue line there are the average concentrations taken from those 24-hour samples. So there are 26 measurements that were collected over a 26-day period. These 24-hour samples were then averaged, which gives you a 1.35 part per billion average concentration in the home, as compared to what Beacon found with our passive sampler, which was 1.29 ppbv of an average concentration throughout that 26-day exposure period, which has an RPD of 5%. Now this Beacon sampler here that I show you here is a configuration that Beacon is also using for soil gas sampling. And we're doing more research to be able to understand better how we are able to provide a concentration for soil gas work using this sampler. And you'll be seeing some research work coming out of that over the next year. So this was the first sampling event. So we have an RPD between the long duration 26-day passive sample showing 1.29 ppbv compared to an average of each of those 26 24-hour measurements of 1.35 ppbv. Very good correlation. So let's look at the second round of sampling. In this round, which was a 22-day exposure period, the passive sampler was kept out there for that entire 22-day period, and concentrations were measured daily with 24-hour samples. And you can see it's compared to the first round where we had concentrations from 0 up to 3.5 ppb. In the second round, they had concentrations from 1 ppb to 6 ppbv. And while there's a lot of variability in the concentrations in this home, because the researchers want to skew it to make it a more challenging site for a passive sampler. Would a passive sampler be able to have an accurate average concentration over a long time period when you have great variability in the indoor air concentration? So if you will, they game the system to really challenge the passive samplers. And so what you can see here is over this 22-day period, once again, Beacon's passive sampler had a 3.43 ppbv average concentration, and the average of the 22 different 24-hour measurements that were collected had an average of 3.3 ppbv, an RPD of 4%. Excellent agreement. The next round, the third round, had concentrations ranging from almost 0 ppbv to almost 7 ppbv. And there, with a 20-day exposure period, once again, the Beacon sampler had an average concentration of 3.04 ppbv versus 2.68 with the daily 24-hour samples, with an RPD of 13%. And the last one that we have data tabulated for. They challenged the indoor air was starting off with a higher concentration and then took it down next to 0 because, of course, we want to see how it performs with this wide variety of concentrations. And here again, 1.86 versus 1.58 for a relative percent difference of 16%. Very good agreement. You'll be seeing the results of this at some upcoming conferences where Dr. Gual will be presenting this data, as well as eventually a journal article publishing information on it. All right, so we've shown you some data to support the uptake rate of the sampler. That's linearity over a long time period. We've shown you the detection limit, how low the detection limit can be for the sampler. Showed you the accuracy of how it compares with Summa canisters and the precision when you're looking at duplicates. We are using this technology for projects, and we're sampling at sites where they're measuring concentrations in homes, they're measuring concentrations in commercial applications. We are using it to measure concentration in sewer gas lines, and we're using it to measure concentrations in ambient air. What I share with you here are some guidance documents that are available, and this presentation will be available for you to write down these guidance documents later, take a closer look at them. But they provide a lot of information on how to collect samples using sorbent samplers. The top one I want to note there, which is highlighted in red, I'm going to go a little more detail on, because that one gives you guidance on how to collect passive samplers for indoor air applications. Here is a summary of some of those guidances that are provided in that document. And you'll see on the right side there are some pictures from some of the work we have done. And if you look closely, you'll see there's sorbent tubes there. This goes to support. These are very unobtrusive. They're not scary to the homeowners, as if you had a shiny stainless steel Summa canister sitting on the shelf there next to their books. And as this client does, they use a chalkboard to record the house number and the location and take a picture of it to show where the samples were collected. But with this ASTM standard, I wanted to go over briefly with you as we're wrapping up here, is guidance of where you should collect a sample. It's the same concept as if you're using Summa canisters or other methods, using common sense as to where you want to collect samples. You want to sample in the breathing zone, and you want to sample at the lowest level of the structure at a minimum. You can sample at different levels, maybe the bathroom, because they can be conduits for vapor intrusion into homes through the piping. But at a minimum, you want to sample in the basement or the lowest level. You want to consider the temperature of where you're sampling. You don't want to put it next to a radiator. You don't want to put it right next to a vent. It's going to be blowing cold air. You don't want to place them in direct sunlight. And you don't want to put them in drafty areas that might dilute the sample compared to what might be the concentrations inside the room. So you want to sample in the center of the room, if possible. And you want to also sample in areas that have sufficient airflow. Don't put them in closets, inside shelves where you won't have air movement. Very important for it to work properly. But this is an ASTM standard. There's other guidance out there that I draw your attention to that I think you would find of use. All right. So with that, I'm going to open it up for questions. I think we have a couple that came in, but I also wanted to note that with radon sampling, which we do here in the United States in areas where radon is concerned, you can't collect radon sample for one day. It's not accepted. We recognized decades ago to get an accurate average concentration, you need to sample for at least 3 days. And that mindset and that approach, we believe, should be applied also when you're sampling for indoor air. So with that, Lowell, I'll open up to questions if you have some that have come in.
Yes, and thanks, Harry. That was a great presentation. I do have some questions. First, I'd like to just make a quick note. We do have time for questions. Encourage all the attendees to ask questions and further the learning for all attendees live and those who end up watching the recording in the future. After the webinar, you will be sent a survey. Please take just a few minutes to answer the handful of questions. If you wish to provide, and those are, yes, no, ABC type questions. If you have time and you wish to provide more constructive feedback, there is space for you to do so. The speakers, and this is true for all of the webinars in the webinar series, They do appreciate any and all feedback, as do the organizers for EnviroExpert webinar series. Again, the whole presentation is being recorded. A link to view and share the recorded presentation will be available and sent to all attendees within a very short period after we are done. So, going to the Q&A session, I have a few questions I'd like to get started with, and maybe this might spawn some additional questions. Harry, have you applied these samplers on indoor air monitoring programs?
Yeah, it's a good question, and I'd like to be able to share some results on that. Of course, they don't like us to share concentration data for people's homes, but we have applied these not only where we're sampling like dry cleaners and one-time residences just to get a concentration, but we are applying these passive samplers to replace what was done historically using summa canisters to get the concentration in homes. And we have one program which we're getting ready to start the next round in, where we sample during the winter months, where it's 300 plus homes, where we'll be sampling in each of these homes using passive samplers, where the samplers will be exposed for 14 or out to 26 days, which is what we did last year. So it is part of a air monitoring program for a community that is built above a solvent plume that's migrating underneath their homes. And each of these homes has to be monitored each year during the winter months to make sure that their concentrations are staying below action levels, or to monitor what the levels are if the homeowners did not permit them to put a mitigation system in, which some homeowners do not allow them to. So we monitor what the concentration is in those homes. So we have ongoing monitoring programs using these passive samplers.
That's great. And then with regards to the samplers, you did mention one of your samplers being for passive soil gas. How do you decide what adsorbents to use, and are they different from passive soil gas versus indoor air sampling?
That's a good question, and it's an important one because not all adsorbents are the same. And some of the trainings I provide, I go in depth talking about the many different adsorbents that are available. And that's one of the things that's driven Beacon to want to do additional research, because we have adsorbents that we'd like to use that do not have uptake rates previously identified for them. There is a body of information out there looking at the different ISO guidance documents that are available. ISO 16017 provides a whole list of uptake rates for various absorbents for individual compounds. So you can take that guidance document, have a sorbent tube with that adsorbent in there, and you're able to have that sorbent tube analyzed and provide you with a concentration because there's known uptake rates. Beacon has other adsorbents that we like to use beyond what is available published based on the research work that we have done. And we've used them both for soil gas sampling as well as indoor and ambient air sampling. And we know their ability to target a broad range of compounds and to be strong adsorbents that will not allow back diffusion of the compounds from the adsorbent once it's absorbed, which is very important. So there's guidance out there, and then what I showed you from that prior slide has some of the guidance that you can use for determining what the uptake rates are. But it's very important to work with a vendor who you'll be using to make sure that you know that they are using an adsorbent that has demonstrated and tested uptake rates for them.
Because I understood they're different for different compounds in terms of efficiency and precision.
That's correct, yes. You have to make sure it's a adsorbent that is properly selected based on its properties for the compounds of being targeted, and the properties primarily is focused on the molecular weight of that compound.
Mm-hmm. You said samples can be analyzed by solvent extraction method instead of thermal desorption. Why do you recommend not using this approach?
Well, thermal desorption is a much more efficient way to get the entire sample onto your system. With a sorbent tube, it traps the compounds on the adsorbent. We put it onto our thermal desorption unit. It heats up the adsorbent and drives a gas flow across the bed of adsorbent, driving all compounds off of it. And that goes on to the system for analysis. With solvent extraction, you take the adsorbent, you pour it out of the sorbent tube or whatever type of sorbent sampler you have into a vial. You pour solvent into it, which is typically like carbon disulfide, a very nasty chemical in itself, not very green to use that. And then you'll mix that up and try to get a perfect mixing of the adsorbent inside of the solvent. And then you pull an aliquot of that solvent out with a syringe and inject that into your system. So you have more opportunity for not having reproducibility from one analysis to the next. And we believe using thermal desorption, and the EPA also believes that, because method 325 specifically states that you have to do thermal desorption. You cannot do solvent extraction to target benzene in ambient air. So we believe that it's a much more efficient and a better approach for doing analysis. Plus, we don't have to use carbon disulfide, which really smells.
Great. And what about what radial type samplers? When would you recommend using radial type sampler instead of an axial sampler?
Well, the radial sampler, that has a much higher uptake rate, can be 2 orders of magnitude higher than an axial configuration sampler. So if you want to get an average concentration over a short duration, say just a couple hours, but you need to achieve a pretty lower detection limit, which the axial sampler might not allow, then that's a good approach for that. As long as your axial sampler will allow you to have enough mass absorbed over your time period, we'd recommend using that configuration, because we believe the uptake rate is more consistent. There's less chaos, because with a radial sampler, it's coming from all sides. With an axial, it only has one opening for the gases to get onto the adsorbent, and it has a controlled pathway from the opening to the adsorbent. So we find that to be just a more reproducible type sampler than the radial configuration. But if the axial sampler won't meet your detection limit, then you would need to look at using a radial sampler, like the Radial sampler, to be able to give you a concentration for a shorter sampling period.
Mm. There's a question
I see one that popped up, which it's a great question. If I could note this one, Lowell.
Mm-hmm.
It says, will temperature and pressure impact the uptake rate? And that's a great question, and it's one that the answer is yes, to a small degree. But with our process, and what we have is a requirement of method 325 also, is that the temperature and the pressure are recorded from a MET station, a meteorological station that's close to the petroleum refinery. So that data is provided to us, and we incorporate the temperature and the pressure into our equation when we were reporting the concentration. And we also are doing that with the research work we're doing at Dr. Paul Johnson's study house, where they're taking the temperature and pressure data continuously throughout the sampling period. So we have actually thousands of data points for the temperature and pressure throughout that sampling period. All right, see another one here is asking about the study where we compared the sorbent tubes to Summa canisters. For the results, it says when you collected the TO15 Summa canister duplicates, were the samples just placed next to each other, or did you utilize a splitter? And in there, we sampled, they were just next to each other. A splitter was not used on the sampling train, but they were only a foot apart as far as where they were sampling the air, and we would expect the air to be consistent within that space. The sorbent tubes that were used out there, they were probably a little bit closer, probably about 6 inches apart when they were sampling. So I would expect, even without a splitter, that you would be able to get reproducible results using either type of methodology. All right, do you see some more questions, Lowell? I'm just looking through some here. It'll take me a minute to read them. I say one question here is, what reference do you use for the air diffusivity coefficients? I don't have one of those offhand to share with you. If you do a search for diffusivity coefficients, you'll find it. But also, let me advance my screen here. Here's my email address. If you send me an email, I will send over to you the list of diffusivity coefficients that we have with their sources. Here's a question about vapor intrusion. Sampling in a bathroom would be vapor intrusion due to a preferential pathway. isn't this an artifact in demonstrating that vapors are entering a structure from the subsurface through vapor intrusion? Yes, I would agree that if the vapors are coming in through a pipe, through a drain that's not properly sealed, any way the vapors get in there is vapor intrusion. And that's why I noted when saying that it's always recommended to sample at the lowest level where you have the most opportunity for vapor intrusion to occur. You can have it in bathrooms and other parts of the house where there is piping that comes in there, where that could be a preferential pathway. And currently we're working with 2 different universities on evaluating the transport of gases through sewer lines, where we're using our passive samplers and putting them in sewer lines and taking time integrated measurements. And we are seeing these compounds that are coming up from contaminated groundwater getting into the sewer lines, and those are preferential pathways. So if you're seeing it in the sewer lines and there's a connection to the house, while there is a water trap, there is a risk that you could have a vapor intrusion conduit from those pipes going into the house. All right, Lowell, we're getting on an hour. So do you see any other questions? I'm scanning through them now, make sure we're covering them all.
No, I think that covers it. I just might add that in terms of vapor intrusion, structurally, when you look at the construction design and the architecture of older homes, it was more common practice to not have sealed the floor or beneath cabinets in the past. And if you tear out old cabinets, there's usually a pretty direct open passageway for vapors to migrate through the wall connection where the plumbing's coming through for the sink or faucet and the drain. And if there's any connection to subslab, and this is usually raised foundation type construction, it's pretty clear pathways and through bathrooms and kitchens and anywhere where there's cabinets and plumbing coming through from beneath the house.
Good point.
Well, I think we're out of time. Any additional questions that are here will be responded to separately. And we'd like to thank everyone for your time. I hope you enjoyed the presentation and the discussion session. Harry, I'd like to thank you for your time and making yourself available to present research work and ongoing studies and some of the proprietary or product development, technology development activities that your company is involved in.
My pleasure. Thank you, Lowell. And again, thank you all for attending the talk today.
If you have any questions or would like more information concerning the use of adsorbent samplers to target VOCs and SVOCs in soil gas or indoor air, please visit our website, beacon-usa.com, or contact us at 410-838-8780.